Welcome back. In our previous discussions, we were talking about the mathematical description of the microstructure of material. And in our discussions, we discussed a few things. We discussed the concept of the local state space, and then by putting together the concepts of local state and the local state space, we also came up with something which we called a microstructure function. And this microstructure function is really the one thing which is going to form the basis for our digital representation of microstructure, which is essential in order to do any form of microstructural informatics, in order to featureize the microstructure of the material. So if you look at the microstructure of a material, what we can basically do is we can divide the microstructure, which is effectively an image, into a number of cells. So in case of the digital image, you can think of each of the pixel of that image to be representing a cell. So supposing I have my microstructure which is defined like this, and supposing then I have my microstructure which has, just for the sake of argument, we can say that it has got two different contrasts. So one contrast is this empty cells, and then the other contrast is where you have this hashed cells. So when we talk about our microstructure function, we tend to write this function in this type of notation. I have a m superscript n and a subscript s. So what does this really stand for? M is your microstructure function, and n basically is going to refer to the state of the microstructure, the local state of the microstructure in that particular cell. So for instance, if we are going to denote this type of filled cells by the number 1, and let us say the empty cell by the number 0, then n can take values either 1 or 0. S over here, this really refers to the cell where we are looking at the local state, where we are sampling the local state. So if I start from this cell and let's say I call it 0, 0, and then as I'm going this side, it becomes 0, 1 and so on. So supposing I am now going to look at this specific cell over here. So this cell, in order to reach here, I have to go 1, 2, 1, 2, 3, right? 3 on the y, and then similarly 1, 2 and 3 on the x. So in this case, what I would write is m1 3, 3 is going to be 0, because this particular cell is an empty cell. This is not a filled cell. When I am writing m superscript 1, it means I am basically writing the probability of finding the state represented by the number 1 in this specific cell 3, 3. So since I do not have this filled cell in this filled state in this particular cell, I write m1 3, 3 as 0. If I were to write m0 3, 3, this would come out as 1, because this is basically an empty cell. Now actually this is a probability, so it will not really be 1. It is going to be 1 over something. So if you look at this particular microstructure, you will see that this is divided into a set of 5 pixels as far as the width is concerned, and again 5 pixels as far as the height is concerned. And then so this value over here is going to be 1 over 25. And as we had discussed earlier, if I now take the sum of m1 across all of those cells, let's just say a comma b, I'm just summing it up. So now you will see that the total number of filled states would be 1, 2, 3, 4, 5, 6, 7, 8. So then if I sum over all of the cells, the probability is going to be 8 over 25. And similarly, if I do the same thing for m0 a comma b, if I take the complete summation, this is going to be 17 over 25. And so the overall sum of the microstructure function is going to be 1, which is kind of telling you that when you are looking at the probability of finding at least one state or other in the entirety of the microstructure, the probability is going to be 1. So this is basically what we were discussing. Now, one of the things we have to keep in mind is when we look at the microstructure, especially if you are looking at a material which is fairly homogeneous, you will notice that the microstructure in the different regions of the material would appear very similar. Visually, when you are looking at it, it appears very similar, but it is not exactly the same. So is there a way in which this type of similarity can be captured? That is an important question that one would need to understand. And therefore, what we do is, when we capture microstructures from different parts of the material, we end up creating an ensemble of microstructure. And as we go forward with the microstructural informatics, we will be starting to work with this type of ensemble. So when we talk of an ensemble like this, we have already defined what this M and S is. M is basically your microstructure function, N refers to the state that we are talking about, and S refers to the cell. So if you think about it, N is talking about the type of local state we have got in a particular spatial region of the microstructure. Now, in addition to that, you will notice that now we have added another superscript ahead of the microstructure function, which we are labeling as J. And this J comes from the fact that we are now working with a bunch of different images of the same material with very similar type of microstructure. So essentially what we are doing is, we are sort of sampling one of the images. So if I specify the value of N and S, then I am sampling only one small region in one of the images from my entire ensemble of microstructural images. Okay. So from here, there's something that we will start to appreciate now, that I can now start creating what I would call an average microstructure. And the way I would create an average microstructure is, I will simply sum over the microstructure function of all of the images that I am looking at in my collection of microstructures, and then divide that by the number of images I am looking at. So that is now going to give me an average value of this microstructure function for any given N and any given S. So essentially, when I am using an expression like this, I am literally calculating the mean of M and S in the ensemble of microstructure that I have collected. So when I'm getting this mean, this thing basically is going to represent the overall volume fraction of the local states which we are identifying as N in the material. Okay. And if you really have a material which is homogeneous, then this volume fraction should be independent of where you are looking in the material. And therefore, one can simply drop the subscript and write F and S simply as Fn. Now, what one can further do is, one could sum over this J, M, and S over all of the images, and then over all of the cells in any given image. And then if I divide this sum by the number of image, and then further divide this by the number of cells in an image, it gives me what we can call a one-point statistic. It's basically a one-point spatial correlation, since this is a measure of what one might expect in any randomly selected spatial bin, right? So when I say spatial bin, what I'm really referring to is the cells in which the microstructure is being represented. Okay. So basically what this thing does is, it allows me to select a bin at random and then compute the probability of finding a given local state, allowing for the entire ensemble of microstructures. Now, this thing is pretty useful because it can give me an idea about the probability of finding one specific phase or one specific local state in a given region of the microstructure, but it does not actually give me any further information in terms of how the phases or how the states are placed relative to one another in that microstructure. And therefore, instead of looking only at this 1-point spatial correlation, we start moving towards the 2-point spatial correlation or the 2-point statistics. And so what we are basically doing over here is we are simply extending the previous concept that we just mentioned, and we are trying to find the correlation between two arbitrarily placed points in the microstructure. And then one of course needs to define those points very well, and this is where we introduce the vector R, which is essentially the separation vector of those 2 points. So the subscript S basically is going to indicate the spatial bins that we are talking about, and R is the vector which is joining the 2 spatial bins. So if I now look at this particular microstructure, and supposing I am starting from this point, so this cell or this bin is essentially 0, 0. So what that means is, when I am talking about this particular cell, the value of S is 0, 0. If I now move over to this gray cell over here, for this cell the value is going to be 0, 2, right? So the value of S over here is 0, 2. R is basically the vector which is joining these 2 cells. It's the vector joining 0, 0 and 0, 2, and therefore here the value of R is going to be 0, 2. Now if I move in a perpendicular direction upward, now I move to a cell which is essentially a 2, 2 cell. So that means the value of S over here is going to be 2, 2. And then if I look at the value of R in this case, the value of R here is going to be 2, 0. So 2 units in the Y direction and 0 units in the X direction. And then from here, if I'm moving to something like this, now I have moved to a value of S which is 1, 2, but then in order to move in this direction, I have to move in a negative X direction. So the value of R becomes minus 1, 0. All right. So by specifying the values of S and R, one can start thinking in terms of the relative placement of different phases. Now what we would want to capture here is, can we develop some sort of a correlation function which will consistently give me the more or less average correlation between any 2 phase, between the placement of any 2 phase in a given microstructure. And this we can do using this particular expression. So this is very similar to the 1-point spatial correlation function, except that we now have a second term. So earlier we were simply talking about summing over J, M and S. Now what we are doing, we are taking a product of J, M and S with J, M, P, S plus R. So here I am trying to look at the 2-point spatial correlation between 2 different phases or 2 different local states. One is N and the other is P. And furthermore, I am trying to look at how well they are correlated when they are separated by a vector of dimension R. So this thing is essentially going to give me the spatial correlation between 2 points which are separated by a vector R. Now you also can see, because we are taking a product of 2 microstructure functions, this term that we have defined over here, FNP RS, is nothing but the conditional probability of finding the state N in the bin S while simultaneously finding the state P in the bin R plus S. Now once again, if we make the assumption that our material is homogeneous, we can simplify this thing a little bit more, and so what we can do is we now take a double summation. So we are summing it not only over the entire ensemble of microstructure but also over every single bin in all of those microstructures, and then I'm sort of averaging it out, which is why I'm dividing by the number of microstructures in the ensemble times the number of bins or number of cells in a given microstructure. So what is now happening is the number of bins that allow the placement of N in S and P in S plus R in the microstructure. So I should write P over here. Placement of N in S and placement of P in S plus R in the microstructure. So this term FNPR is a 2-point spatial correlation or 2-point statistics which is correlating two local states N and P in that given microstructure. Alright, so you can now start computing the 2-point statistics for each of the cells, for each of the local states, right? So each of this 2-point correlation is one of the features that you can add in order to describe the microstructure. So just think about it. If we are looking at 2-point statistic as features, and let us say that we are looking only at a unit vector separation, we are not even looking over multiple separation ranges, we are only looking at a unit separation. Even if your microstructure is so small and so blurry that it has basically a 8 by 8 image, this microstructure is now going to have 64 features. Now start thinking about it. When you are capturing a SEM image or a TM image, many times you will find that the micrographs might be 380 by 512 or something like that. So you can start imagining that when you try to featureize the microstructure, you will be having very large number of images. So 380 times 512, that's a pretty big number. And then when you consider, if you are looking at 2-point statistics over multiple phases and multiple spatial correlation, you can imagine how fast the number of features which describes the images is going to go up. So this is going to become unmanageably large, and therefore this is where we have to do some sort of data dimensionality reduction, and for that we use a technique called the principal component analysis. Once we do the principal component analysis of all the features which are describing the microstructure, we will end up finding a few principal components which will now be recast as a new set of features. So this new set of features will be much smaller number of features, and these will still adequately describe the microstructure. So that is basically going to be the idea behind the principal component analysis, and that is what we are now going to look at next. Having started our discussion on the representation of microstructure and then talked a little bit about the single point spatial correlation and the 2-point statistics, it is now fairly obvious to us that in order to featureize the microstructure by considering only this 2-point spatial correlation type of functions, we will end up with very large number of features. So depending on how big our data set is, and as we have been stressing repeatedly, many of the data sets and materials happen to be relatively small. So if we end up doing machine learning with so many large number of features, it can be a problem, and it would be really unmanageable in order to do the machine learning part efficiently when the number of features are so large. And therefore, one of the things that we have mentioned, that we need to do some sort of a dimensionality reduction. We need to reduce the number of features, and for that we mentioned that we use a method called PCA, which is short for principal component analysis. So let's take a look at what we really mean by principal component analysis by taking a very crude example. So what we have here on the left hand side is data which is there in 3 variables, and this data is fairly scattered, and of course visualizing something in 3D is a little bit of a challenge. Now of course in practice for machine learning problems, if you have like 3 sets of features, it's not a problem at all. That's not large number of features. In fact, you would actually want to add some features. Practically you will have way more than 3 dimensions or 3 features. However, starting with this 3-dimensional thing is easy for us because it helps us visualize. So on this case, in this first figure, we basically have 3 features, which are varying along x, y and z. And we have a fair amount of scatter in the data. So what we then try to do is we will want to try and reduce the number of features. So from 3 features we are trying to go to 2 features. So each feature we call principal components. So principal component 1, which we are representing by alpha, and principal component 2, which we are representing by beta. So many of the times this principal component analysis will basically find you some sort of relations which goes like alpha is m1x plus m2y plus m3z. So basically the principal components now becoming a linear combination of the initial set of features that you had. And similarly beta might end up becoming n1x plus n2y plus n3z. The idea is when you reduce your data dimensionality by expressing the data in terms of principal components, which are combinations of the original features, then there may be a chance that you start seeing some sort of trend in the data. And these trends are really what we are looking for. So the idea therefore is to start with large number of features, express those features in terms of smaller number of relations, which are basically linear combination or some sort of combination of the original features, in a way that when you now start plotting it out, you will get some sort of a trend in your data. Now, as far as principal component analysis is concerned, we need to be familiar with a few terms. So first, of course, is what the mean value is. You sum up all your variable and you divide by the number of variables that you have summed up. So that's your mean. And then you've got the variance. So variance basically means that from every observation you are subtracting the mean and then squaring that, and you are summing it over all the observations and dividing by n minus 1. So this is the variance, and then root over of your variance is what is going to give you a standard deviation. And then of course you can also have a covariance matrix. Now when we are doing principal component analysis, what we are basically trying to do is we are trying to maximize the total variance that we have got in our data. So in order to exemplify how principal component analysis is done, I am going to take up one data set. This is the IRIS data set. This data set was compiled by Ronald Fisher. It's now openly available online, and in fact this is one of the data sets which are loaded by default in scikit-learn. So this is something which is a very useful tool for people to start working with principal component analysis. So basically what the IRIS dataset has is it contains information about a variety of different types of iris flowers. So here we have some examples like setosa, versicolor, virginica and so on. And this dataset is then featurized in terms of the sepal length, the sepal width, the petal length and the petal width. So petal, you all know, sepal is basically this green leaf-like structures which protects the bud of the flower. And then it looks like you have some form of correlation which is happening with different features that are shown over here. So you can now start exploring the data in a number of ways. So you could start using this K-means clustering type of thing and then see that you have got 3 different clusters. When you are looking at the species, you will then see that the data is a little bit more mixed. If you use K-means clustering, you will now start to separate the data a whole lot better. But as you notice, it's still not going to be a perfect separation. It is better than just looking at the raw data, because here you have a lot more overlap, lot more of scatter, I would say, in the data. Okay. So if you now start and visualize the data, it is in 3 dimensions. This is how it is going to look like. And the way you can do this, let me actually illustrate with a little bit of a Python code. Hopefully you guys all have some idea about Python programming. But nonetheless, when I'm writing the code over here, I am actually going to walk you through the code and tell you what is basically happening. So this first part of the code, where you have all of this import commands, here what we are doing is importing the appropriate modules. So matplotlib is needed in order to do the plotting. We are importing NumPy. We are using scikit-learn for the machine learning part, and so what we are doing is we are from the scikit-learn we are importing the data set, because that is where the iris data set is stored. After that, the next thing that we will do is we will load the data set and we will start assigning the target values. So from this iris data set, we will now have the X, which is basically the data and the features, and then on the Y, which is basically the target value when we are trying to do the principal component analysis. Okay. After that, what we are basically doing is we are setting up the script for doing the principal component analysis with 3 principal components. Okay, and then what we do is we will essentially go ahead and plot it out. And so as we plot it out, you will get a plot which looks like this. And what you now notice is you are able to separate out the different species of iris by using this principal components. So you have, after you are doing the first this principal component analysis, now you are able to start identifying and start separating out the data that belongs to the 3 different species of iris. So this is something which is pretty useful, because what we have done is we have started with a data set which had multiple features. So sepal length, sepal width, petal length, petal width, that in itself will give you quite a few features. And then after that, what we basically did was we did a principal component analysis in order to do this data dimensionality reduction. And after we were doing the data dimensionality reduction, we ended up with 3 principal components. So basically less number of features, that is or less number of components, that is describing the data. And by doing so, we are actually able to separate out the different species of iris or the data corresponding to the different species of iris. So this is the way in which one can go about doing data dimensionality reduction before you start your machine learning process. Now, this type of thing can actually be applied to the materials problems as well. So what I have over here is a database about different types of semiconductors. So aluminum nitride, aluminum phosphide, gallium arsenide, indium nitride, all of these are different semiconductors. And then how do we start featureizing the semiconductors? We have the atomic number. So obviously it's not just the atomic number. This is basically what you are pulling out from your composition based feature vectors. So these are the average atomic numbers. Similarly, the melting point is the average melting point. The valence electron is also the composition weighted average number of valence electrons. Then what we are also looking at is the difference in the radii. So radii, in the case of aluminum nitride, we are looking at the difference between the atomic radius of aluminum and atomic radius of nitrogen. We are looking at the averaged electronegativity, and we are also using the lattice constant. So in this, like a toy type of data set itself, you can see that we have already described our semiconductors by using 6 different types of features. Now, if you look at the plot of the features with respect to each other, you will see that you don't necessarily see a lot of information when we are looking at this type of pair plots. So for instance, in these cases, obviously they are correlated to themselves, and therefore you actually have a perfect relation along the diagonals, which is what we had seen earlier as well. But then if you look at the other regions, you don't have any particular relationships between the features which are standing out. So manually doing dimensionality reduction here is going to be a challenge, and that's why we start using something like a principal component analysis. And so what I'm going to show you over here is what happens when you take the data and you try out principal component analysis with different number of components. And here what we have done is we have reduced the problem to two components. So I have a x2 prime component and a x4 prime component. And when you look at this data over here now, you can start seeing some sort of a trend. Now, of course, the trend is not perfect. You will see that some of the points are lying below this line with a slope of 1. Some of the points are lying above with the line, and so on and so forth. So they are not exactly lying on the line. So it's not a perfect correlation, but you can actually see that these two principal components have some sort of a relation, and you can actually start capturing some of the trends in the data by converting the original features into two principal components. So as we go forward with our microstructure modeling, this is basically what we will keep on doing. We will be featurizing the microstructures using 2-point statistics, and then we will be reducing the number of features from all of these 2-point statistics into a smaller number of principal components, and then the machine learning is going to be done with those principal components. So with that, we are going to stop here for today. Thank you very much for joining.